few minutes ago.
I was gonna say, like, well, I hope you got it because he's leaving town. And coming back.
It's about time for us to get started. So let's go ahead and do so. I think this is our 27th video lecture. I'm not sure, but I think that's what it is. We are talking about limits of functions, and we had just gotten through showing, I believe, that if there is a limit for a function at C, that limit is unique. There can only be one. I think that's what we ended with.
In the middle of the proof.
We were in the middle of the proof.
Yes, sir.
We haven't done that. Oh, well then let's start there. So let us recall. That's great. Thank you very much, everyone. John, thank you. That we have this theorem. It says let A be a subset of R. F go from A to R. And C be a cluster point. Of that. Then F can have at most one limit at C. And the proofs by contradiction, we've done part of this before.
I have written down that if the limit as x goes to c of f of x exists, then that limit
It's unique.
is the same.
Same idea.
Is it-
Same
Okay.
means the same. And if you'd like, we can write down the exact same.
Well, I just didn't know which one you would want for.
It means the same, but let's be consistent. So. Then the limit is unique. Thank you very much, John. And remember, the limit is the L, which this limit is x goes to c of f x equals to. It's got to be one thing. And we're going to do this proof by contradiction. So, Alfred, that is the way that I looked at it last time?
A contradiction?
No, ma'am, the statement. Yes.
Did you write down the let A be a subset of wheels?
We didn't
Because
have that part,
I just
but-
have if the limit of f of x exists. Maybe I didn't write it
That's-
down, maybe
No, I generally don't write that first part, but it is something formally that's part of it.
Okay, well, I'm writing it down.
If you're even talking about that limit, you have to have those conditions.
That's exactly right. So the proof is by contradiction, and so we assume there exists L1 and L2 such that the limit as x goes to c of f of x equals to L1 and the limit as x goes to c of f of x equals L2. And I'm going to say the setup afterwards, where a f of x, or f goes from A to R, and C is a cluster point. Of A. And L1 is different than L2. That's what we said. Okay. Without loss of generality, since these two numbers are different, we'll say L1 is less than L2. So, what we'll note is that L2 minus L1 over 2 is a positive number. So L2 is bigger than L1. That means L2 minus L1 is an element of positive numbers. That's by definition of less than. And so if you divide a positive number by 2, that's a positive number you get something. So since the limit as x goes to c of f of x equals to L sub 1, with this being considered as our epsilon, we say there exists a delta sub 1
greater than 0, such that for all x in A with 0 less than the absolute value of x minus c less than delta sub 1, then the absolute value of f of x minus L sub 1 will be less than L sub 2 minus L sub 1 over 2. And I think that's probably where we left off last time. Okay, so that's where that means, so all these comments that I'm making, Chuck, are for the x's in A that satisfy this point. So John, we're not talking about all x's. We're just talking about this. So for all x element of A with 0 less than x minus c less than delta sub 1, then for those x's, here's what I could say. Rewriting that inequality that involves absolute values is a compound inequality without absolute values. We'll have the negative of that positive number, which will be L1 minus L2 over 2, is less than f of x minus L1 is less than L2 minus L1 over 2. And what we're going to do is we're going to solve for f of x. Yes, ma'am?
Is it L2 minus L1, or did something happen?
Okay, something happened. So, Audra, what happened was is that we have something inside absolute values that's less than this positive number.
Okay.
So that's like the statement. I know people in the Hamilton
Oh, it's
say.
the negative. You incorporated the negative.
Right.
I got it. Okay.
Good. Now remember, what are we talking about? We're talking about just for the x's, Chuck, in A with 0 less than the absolute value of x minus c less than delta sub 1. Just for those, then if I solve for f of x, what I would do is I would add L sub 1 to both sides, or to all parts of this compound inequality. I'm just adding, this is just algebra, I'm just adding L sub 1. When I do, really that's adding 2 L sub 1 over 2. 2 L sub 1 over 2, so they have common denominators. 2 L sub 1 over 2. And what you get on this side, would you get 2 L sub 1, so it'd be 3 L sub 1 minus L sub 2 over 2 is less than f of x, which is less than, here I'm adding 2 L sub 1 over 2. I get L sub 2 plus L sub 1 over 2. So that's the statement. I'm going to kind of star it. We're going to come back to that statement. Well, I got that result because we knew that f of x converged to L sub 1 and c. But we also are assuming that f of x converges to L sub 2, Jeff. So I could say similar statements. So similarly, again, the L sub 2 minus L sub 1 over 2, that's like my epsilon. But I'm going to say similarly, since the limit as x goes to c of f of x equals to L sub 2, then there exists another delta. Maybe it's not the same delta. Let's call it delta sub 2. It's greater than 0, such that for all x in A with 0 less than x minus c less than delta sub 2. So for just those x's, because of the limit as x goes to c of f of x equals to L, we have an absolute value inequality involving L sub 2. I'll write it down in just a second. Okay, so for those x's, we have absolute value of f of x minus L sub 2 will be less than L sub 2 minus L sub 1 over 2, that positive number. So again, for all x's, we're just talking about certain x's. For all x's in A with 0 being less than x minus c being less than delta sub 2, then rewriting this inequality that's above my hand as a compound inequality not involving absolute values, we'd have L sub 1 minus L sub 2 over 2 less than f of x minus L sub 2, which is less than L sub 2 minus L sub 1 over 2. And then if I solve for L sub 2, so again, it's for all x element of A with absolute value, well, 0 less than absolute value of x minus c less than delta sub 2. Then, here, adding L sub 2 to both parts, or all parts, all three parts, of this inequality, that's the same thing as adding 2 L sub 2 over 2. We get the following. We get L sub 1 plus 2 plus L sub 2 over 2. It's less than f of x. It's less than 3 L sub 2 minus L sub 1 over 2. I'm going to call this double star for a second. And for those of you who are here in class, if you look at the board at the same time at the star and double star, there's parts of it that are inconsistent. So here, f of x is less than the 2 L sub 1 L sub 2 added together divided by 2. It's less than in this part, okay, f of x is. And here, f of x is less than it again. So I did something goofy. Let me look here. So I added L sub 2.
No, you did it right.
That's right.
Yeah, that's right. So here, it's bigger than, f of x is bigger than it over here, and it's less than it over here. But the problem is, really isn't a problem, but to be more precise, both of the statements, star 1 and star 2 statements, are applying to different x's. One of them are for x's within delta 1 units of c, except for possibly c, and the other statement is for x's within delta 2 units of c, except for possibly c. Okay? We'd like to have one statement for the x's that one statement for a particular type of x's, not for different x's. And I had said this to you, and you probably might remember, that when we had different k's involved in sequences, we went to the maximum to have both of them happen. Here for limits of functions, what we were talking about things happening for values close to c.
We'll make it as close as possible.
So we want to make it as close as possible. So instead of taking the maximum delta, we take the minimum delta. We make sure that we're within the closest region of C that we need to be in. So here, we let delta be equal to the minimum between delta sub 1 and delta sub 2. And then, for all x element of A with 0 less than x minus c less than delta, we got two statements. So I'll write down both statements. Gosh. I'm going to go ahead and write it down. So the first statement is that 3L sub 1 minus L sub 2 over 2 is less than f of x. I'm going to. Yes.
Oh, okay.
Thank you very much. Plus L sub 1 over 2. So that's the first thing. Yes, I know. I need to move the camera. Thank you. You didn't do anything wrong. I'm grateful to be reminded. That's nice of you. Okay, that statement that I just wrote, it came from the star statement. Okay? And we're talking about the same x's here, and the ones that were within delta units of C, but not including C. The second star statement is still on the board, so I can look at it. It says L sub 1 plus L sub 2 over 2 is less than f of x, which is less than 3 L sub 2 minus L sub 1 over 2. And these parts of these statements, both of them have to happen, but they're contradictions of each other. F of x is less than this number, but f of x has got to be bigger than that number. That can't happen. You can't have a number that's both less than and bigger than the same number. So this is a contradiction. So we must have assumed something incorrectly. So what we assumed incorrectly there was more than one limit. So there can only be one limit. That is, the limit must be unique. If it exists, is unique.
So that ends the proof.
And it's very similar to the proof that we had for the limits of sequences being unique. There can only be one. Okay. So that ends the proof that we were in the midst of when we ended class last time. So I'm glad to get that done. But at this point, I want to stop for a second and remind you, we have a homework assignment Wednesday. Friday. So that's next time. So why don't we give everybody a second to ask any questions that you might have about the homework? Anybody have? Yes, ma'am.
You did an example for 2B, but I was wondering about 2A. I plotted the sequence, and I know that it's not the it's not my time.
Okay, so I was just telling us for
I'm
2A, nothing to be sorry about. She
It's
said the
not.
answer is it's not my time. Okay, that's right.
I guess I'm asking for the approach. Would I show that it's a contradiction that it's increasing and that it's a contradiction that's decreasing?
Right,
and
I
therefore-
would. So let's look at this, we're talking about sequences, right?
Right.
So let's look at -1 to the n as an example. So here, this is x sub n. Is what I'm symbolizing it by. And my output values are -1, 1, -1, 1, -1, 1, and so on. Okay? And this guy is x sub 1, and this is x sub 2, and this is x sub 3, and x sub 4, and x sub 5, and x sub 6. So here's what I would say. I'd say, note, -1 to n is not a decreasing sequence. Okay? Because x sub 1 is less than x sub 2. So it's not decreasing. Okay? It isn't the case that for each n, x sub n is greater than or equal to x sub n plus 1. It's not greater than or equal to x sub 2. Okay? That's not happening. Also, -1 to the n is not an increasing sequence. And the reason it's not is because if you compare x sub 2 with x sub 3, x sub 2 is bigger than x sub 3. Okay? So this is not happening. It's that x sub 2 to be decreasing, to be increasing, this is what would have to happen. To be increasing, x sub 2 would have to be less than or equal to x sub 3, and that's not happening. Is that okay? So it's not increasing, it's not decreasing, so then it's not a time.
And this is analogous to the type of work you're expecting for
Yes,
this
ma'am.
particular
Yes, ma'am.
one. All right.
That's the one with the sign?
Yes.
Yes, ma'am. Is that okay?
Yes.
Thank you for asking. Would anybody else like to see something or ask something from the homework? I think, yes, ma'am, Meg.
You said that there were ends before mine.
Yes, ma'am, would you like to hear? Okay. So let's talk about 4 and 5. So for 4, Fourth, it says suppose that every subsequence of x sub n has a subsequence that converges to 0. Show that x sub n itself must converge to 0. And my hint for 4 is this. Use contradiction. That's my hint. And that there's a theorem, Megan. The contradiction will say, we're trying to show that x sub n converges to 0, right? The contradiction assumption would be, suppose x sub n doesn't converge to 0. And then there's a theorem that we proved not that long ago, that if a sequence doesn't converge to a particular number, then that's equivalent to two other things happening. One of which is that there exists a sequence that always stays epsilon naught units away from 0 in this case. Does that make sense what I just said? So that's going to lead to a contradiction. So there's a theorem that you can use. Megan's okay what I said? Melissa, is that okay? Is that okay with everybody else? Okay. For problem 5, it says suppose that x sub n, so we determine the sequence, is less than or equal to 0, and the limit as n goes to infinity of minus 1 of n x sub n exists. We want to show that x sub n converges. So here's my hint for problem 5. Is to argue that since the limit as n goes to infinity minus 1 to the n x n. We know it exists, okay? It's some number, x. But I'm going to tell you what number it is. It's 0. So you prove that that's 0. Okay? And then you can show, from this you can show the limit as n goes to infinity of x sub n has to be 0. The argument to show that the minus 1 of n times x sub n has to be 0 is a kind of subsequence type of argument. In that we know that the limit is minus as n goes to infinity, minus 1 to the n x to the n exists. Okay? So that means that every subsequence of it exists, converges, I'm sorry. Every subsequence of it converges. And converges to the same thing as this sequence does. Okay? So in particular, when n is even, it converges to whatever it's supposed to converge to. When n is even, the subsequence converges to, let's call it x. Okay? When n is odd, the subsequence of this sequence converges to x. And then you can tell about the signs of x. And you'll see that it has to be 0. Okay? That's what I have. If you need further description, you let me know. That's what I have. That's the way that I would do it. Or that's the way I have it. Anything else? Okay. Well, as I raised the board, I said I was sometimes a little too cute, in terms of my comment, too smart out in terms of my comment. Wearing a suit today. You look nice. You always look nice. I had a friend, Scott Rayburn is his name, and I like him very much. He's a very nice person. And he told me, he said, one time I was so smart alecky that I cost myself something and hurt a relationship that I had with one of my family members. And I'll tell you the story when we move on. I said, what are you talking about? He said he had an aunt that for every birthday that he had for some period of time of his life, she gave him $5. He said when he was 7 years old, and it was 1976, and his aunt gave him $5. Well, that was like a month and a half worth of candy. You buy a lot for $5 in 1976. So it was fantastic. He said when he became, 21 years old, and she gave him $5 for his birthday, it wasn't as big of a deal. So on his 21st birthday, she gave him $5. He said, and what are you going to do with it, Scott? He said, well, I'm going to put a down payment on a house. He said, I said, well, that didn't go over very well. No. I said, how did you tell? Did your aunt get mad? She said, no. He said, no, I can tell she got mad, actually, but he said, I never got another $5 for my birthday. I never got anything for my birthday.
So here was a person who always remembered me, and I said something smart aleck to her, and that was it. So he said, well, I wish I'd never opened my mouth, because it's always nice that she was thinking. All right, anyway, that's my story for today. One of my stories for today.
Next thing I want to do is list a fact from the text about limits. And it's this theorem. It says if we let F go from AR and C be a cluster point of A, then the following statements are equivalent. One is that the limit as x goes to c of f of x equals to L. Two, given any epsilon neighborhood of L, let's call it V sub epsilon of L, there exists a delta neighborhood of C, let's call it V sub delta of C, centered at C, such that for all x element of A intersects V sub delta of C, then what we get is that f of x is an element of V sub epsilon of L. And I've made one mistake here. Such that for all x different from C, element of A. These follow each other simply from the definition of what it means for the limit as x goes to C of f of x equal to L. That's the reason it comes true. Let's take a look at it. The book doesn't provide proof here because it's an immediate consequence of that definition. Let's go ahead and do it. Excuse me. Is everything printed okay? Can you read it?
Symbol between A and B, that's the
Intersection.
intersection.
Yeah, intersection. That's what they have in common. Everything that's in A is also in this delta neighborhood.
So we would write it for all x different from C, there's an element of A.
And an element of, right. So that's what that intersection means. An intersection means it's in both. Okay, so to prove this, it says two statements are equivalent. So here, let's get the proof started. We're going to let F go from A to R and C be a cluster point. Now, really, when we say two statements are equivalent, that really means that they're if and only if statements. That's all it means. So here, we're going to go in this direction. One implies two. So we'll suppose the limit as x goes to C of f of x equals to L. What we've got to show is that anytime you take an epsilon neighborhood about L, there's this delta neighborhood about C, such that for every x in A intersect C with x being different, every x in A intersect the delta neighborhood about C that's different from C, then f of x will be in the epsilon neighborhood. So here we let V sub epsilon of L be an epsilon neighborhood of L. We must show there exists a delta neighborhood of C, let's call it V sub delta of C, such that for all x different from C, for all x element of A and being in this neighborhood, with x being different from C, then f of x is an element of V sub epsilon of L. Good.
I have a question.
I'm ready.
Is this for every delta also?
Is it for every, no, there exists.
Okay.
So
Oh, no, that's right. Never mind.
So the epsilon, it doesn't matter what epsilon's given to me, there's a delta that depends on that epsilon. And it might depend on the C.
Okay.
What's that delta? I'm sorry, that's delta. Epsilon neighborhood of C, V sub delta of L.
Epsilon neighborhood, it should say a delta neighborhood. Where am I looking?
I'm sorry, it's the second line up. Epsilon, delta neighborhood of C.
I'm here. Tell me where to go.
One up, right there, that symbol.
Is-
Delta,
Delta.
sorry.
Nothing to be sorry about. I'm sorry. My handwriting was so bad.
Are they still being different from C?
Yes, and here's where I put it this
Okay,
time.
all right.
That's right, we do. Good.
Okay.
Okay, so since the limit as x goes to C of f of x equals to L, and we've been given an epsilon, because we got this epsilon neighborhood about L, there exists a delta greater than 0 such that for all x element of A with 0 less than x minus C less than delta, then f of x minus L will be less than epsilon. I was given the epsilon already to make the epsilon neighborhood. So, we're talking about x being in A, and the distance between x and C being less than delta. That's what we're talking about, okay? Look, if x is in A, then it's in A. And x being an element, well here, if x minus C is less than delta, then that means that x is an element of the delta neighborhood about C, because the delta neighborhood about C is all the numbers whose distance from C is less than delta. This part right here generates this part. We already got x as an element of A. And then, this part right here, that 0 is less than the absolute value of x minus C, tells me that x cannot be C. Because if x were C, C minus C is 0. And you don't have 0 being bigger than 0. So we're saying, hey, this restriction right here, the 0 less than the absolute value of x minus C, says x can't be C. Then, f of x is a number, okay? And what property does it have? It has this property right here, that its distance from L is less than epsilon. Well, what does it mean to be, for your distance from L to be less than epsilon? Well, it means you're in the epsilon neighborhood about L. So, epsilon neighborhood, we've been calling it V sub epsilon here, about L. And so, for all x element of A intersect V sub delta of C, I got this delta works, with x being different from C, f of x is an element of V sub epsilon. So that's part of the proof. Now we have to go in the other direction.
So we have to show that the second statement implies the first.
Okay, so the backwards row is that we're going to assume, suppose, for each epsilon neighborhood of L, we're supposing this far, we're going to call it V sub epsilon of L. There exists a delta neighborhood, V sub delta of C, such that for all x element of A intersect V sub delta of C with with x being different from C, then f of x is an element of V sub epsilon of L. That's what we're supposed to do. Well, what do we want to do? We want to show. I don't know how it is for you guys, but it's a little bit hard for me to keep up with what we're doing, what it is we have to show. But what is it we have to show? We have to show that the limit as x goes to C of f of x equals to L. No, that's what I got to show. To prove this. And so the way that we're going to show that the limit as x goes to C of fx equals L is using the definition. Okay? So I know what the definition says and the kind of the framework for proving the limit as x goes to C of fx equals L. We say let epsilon be greater than 0 b. Okay. What am I looking for? Yeah, I need a delta. For all x in A with 0 being less than x minus C being less than delta, then what will happen? This is what we need to have happen. We'll need the absolute value of f of x minus L to be less than epsilon. Okay. So we want absolute value of f of x minus L to be less than epsilon. That's what we want to have happen. But for the distance between f of x and L to be less than epsilon means that f of x is an element of the epsilon neighborhood about L. Is that okay? That's what we want. But look, I've been given an epsilon. And we know by assumption when I say by assumption, I mean in the backwards direction of the proof we're trying to do, the statement we're trying to prove, backwards direction. That we're being given an epsilon and we want to show that f of x is an element of the epsilon neighborhood of about L. Well, we know that anytime you give me an epsilon neighborhood about L, I'm giving you this one. I want to show that f of x is in here. I'm giving it to you. By assumption, we know there exists a delta neighborhood. So here it would be C, V sub delta of C, such that for all x element of A intersect V sub delta of C, with x being different than C, then f of x is an element of V sub epsilon of L. So, for all x element of A, with, so look, to be in A intersect V delta of C, to be in the intersection, you have to be in both of these sets, A and the delta neighborhood by C. Have to be. So, first of all, you got to be A. So for all x in A, not just for those, we're going to narrow it down. We're going to narrow it down because we're going to make sure that the x's that we're talking about that are in A are also in here. So what does it mean to be in here? It means that your distance from C is?
Less than delta.
Okay.
We know it has to be bigger than 0 also,
Why do I know it has to be bigger than 0?
because x is different from c.
And now because x is different than C, I know this has got to be bigger than 0. Then, so I'm just translating this statement, this part of the statement that we know to be true from something right here, that for all x, element of A intersect V sub delta of C with x being different than C. I'm rewriting it as this statement. They mean the same. They mean exactly the same. Then f of x is an element of V sub epsilon of L. Well, what does that mean? Well, the situation from which we're talking about stays the same. So, for all x element of A with 0 less than x minus C being less than delta, then for f of x to be in this epsilon neighborhood about L, that means its distance between f of x and L is less than epsilon. And when that happens, that means that the limit as x goes to C of f of x equals L. That's the definition. So thus, the limit as x goes to C of f of x does equal to L. And that's the proof. Oh yeah, we're done. Well, the next theorem is a huge theorem for our class. Important theorem. And I had mentioned in a roundabout way this theorem. And that I said we're going to learn about limits of functions and we're going to relate them to limits of sequences. And that's what this guy does. So here's the fact that we're going to prove next. It's got a name. It's called the sequential criterion for limits.
That just sounds important.
It sure does, and it is.
That word criterion.
Yes. I agree. It's a powerful word. The sequential criterion for function limits. So here it is. It's a theorem, okay? Here's what it says. It says, let F go from A to R. The domain of F is A. Yields out real numbers. And C be a cluster point. Of A. Then, the following statements are equivalent. Excuse me. One is that the limit as x goes to C of f of x equals to L. So L is some real number. Two, if x of n is a sequence in A such that x sub n is different from C for all n element natural numbers. So none of the terms of the sequences are C. And the limit as n goes to C, as n goes to infinity, of x sub n equals to C. So we're talking about if you give me any sequence from A whose none of its terms are C, but they converge to C, then the sequence, this is a sequence, okay, f of x sub n, that's a sequence of numbers, output values. They, as a sequence, they converge to L. So this theorem is going to allow us to relate limits of functions to sequences. So what's it saying? It's saying, hey, the limit as x goes to C of fx equals to L if and only if every sequence within A that converges to C, where none of its terms are C, has the property that f of that sequence, which is a sequence itself, converges to L. So the output sequence converges to L. This class ends in another hour and a half, something like that. I don't know.
We're actually allowed to leave now, aren't we?
Say that again.
We're actually allowed to leave now.
Well, we're not far from it. I think I have time. We've got 2 minutes. I have time to get started. Listen, I know it's ridiculous. I know. But this is the way I was trained. I mean, you should have seen how big of an emphasis it was when I was in grad school. Don't let them go early, John. Don't miss class. That's what they tell me all the time. You don't miss. I walk in and hadn't slept at all. I was out playing cards, studying, something. Today we're going to learn about the law of science. I was teaching calculus. It's not even the right topic. Anyway, but they learned something. But that's what would happen. Okay, so here's the proof. Here's what we do. We let F go from A to R, and C be a cluster point of A. So that's the setup. Here's this direction. We suppose the limit as x goes to C of f of x. What is it we want to show? What we want to show is that if you give me any arbitrary sequence in A, none of its terms are C, but it converges to C, then f of that sequence has to converge to L. So what we're going to do is going to say, let x of n be a sequence in A with, we're almost done. I'm going to take one more second. X of n being different from C for all n element natural numbers. And the limit as n goes to infinity of x of n equals C. We want to show, I just want to tell you what we want to do. We want to show the limit as n goes to infinity of f of x of n equals to L. That's what I want to show. We'll start with this next time. That's what I want to do. Hey, I want to show a sequence convergence. So I'm going to be given, what am I going to be given? I'm going to be given an epsilon. I'm going to be looking for a okay. It's kind of a change of pace because we've been working, here's an epsilon with limits of functions. We need a delta. Let's do it. Okay, thank you very much.